All right. Good evening, everyone. My name is Hendricks, and I'm a teacher at Providence St. School. And I would like to use the next maybe 40 minutes or so to talk about a math topic that I think I'm pretty excited about. I think it's very relevant, very applicable to some of the things that students can do with math. You always hear, how does this relate to real life? I hear that quite a bit. And I think this is a topic that we can definitely relate to everyday life. It's called coming up with a best fit line. We did talk about it last week, but I'd like to add to that. I'd like to add to that a little bit more. Hopefully you find it interesting. Let's just jump right into it. What we have here is, let's say we have some data. All right, so it's some data, X and Y are variables you tend to see. X and Y are variables you tend to see. And X could represent anything. X can represent weeks. After 2 weeks, you have, 3 friends, let's say. After 2 weeks, you have 3 friends. X can be any independent variable like time, weeks, days, months, years. And Y could represent anything. Y could be the value of a stock. Y could be a distance from home. Okay, so, but for this particular problem, let's just say after 2 weeks, we have 3 friends. Right? After 6 weeks, we have 6 friends. Okay, so we'll just use weeks and friends as our identifiers as to what these variables represent. What I'd like to do is I'd also like to graph. I'd like to graph these points. So at 2, let's say we have 3. After 6 weeks, we have a 6, let's say. After 10 weeks, we have 9. Hopefully you see how I'm plotting these points. I could even extend this if I wanted. I could extend this 11, 12, 13, 14. After 14 weeks, let's increase this a little bit, so we have 12. All right, so what I'd like for you to see is we have a perfectly linear situation here. And what we'd like to do, we did this last week, what I'd like to do is I would like to come up with a linear model. Sometimes it's called a linear model. Sometimes it's called a linear model. Sometimes it might also be called a linear regression equation. Linear regression equation. Actually, let's not call it a linear. Sometimes it's called a let's just stick with a linear model. I'm sorry. A linear model or equation. Sorry about that. All right, so let's come up with an equation that represents this data. Those terms that I used earlier, regression equation and best fit line, we'll talk about that a little bit later. I don't want to use those terms quite at this moment. All right, so let's come up with a linear model or equation for this data. And the reason why we want to maybe come up with an equation for this data is to answer questions like, how many friends will we have after 100 weeks? Do you really want to count up to 100? 2, 6, 10, 14. Do you really want to count up to 100 to answer this question? I think not. Or the question could be, how many weeks would it take to have 1,000 friends? It would be difficult to count by threes up to 1,000. So this is why we want to have an equation that models this data. We want to produce a linear model that represents this data so that we could what's called extrapolate or forecast or predict what's going to happen in the future. Let's come up with a linear model, and I think you'll see the benefits, all right, to having it. All right, so what you could do here is you could find the slope. Slope is the change in y over the change in x. Okay, change in y over the change in x. And it doesn't matter what pairs of points you use. Let's just use the first two here. Let's take 6 minus 3 over this 6 minus 2, and you end up with 3 over 4. All right, so you end up with a slope of 3/4. You're rising to go from this value to this value, rising up 3, and you're running over 4. So the slope is 3/4. All right. And what we're going to do after that, after we have the slope, is to find the y-intercept using the slope-intercept equation. Y is equal to mx plus b. It's called the slope-intercept equation. Or you could use something called a point-slope equation. We'll use both. Point-slope equation. Right? That point-slope equation is y minus y1 is equal to the slope x minus x. All right. So we've got the slope of 3/4. Now you can choose any point that you want. Let's choose a point 2, 3 along with the slope to find the y-intercept. So we have y is 3 is equal to the 3/4 times x, which is 2. We're using this point right here, plus the y-intercept, which we need. We end up with 3 is equal to 3/2 plus the y-intercept b. And subtracting the 3/2, 1.5, you end up with b is equal to 3/2. So what you end up with is an equation, put it right here, of y is equal to 3/4 x plus 3/2. That's the equation that represents this data right here. All right. You could also come up with that same equation using what we call a point slope form, where you have y minus a y value on the line. Let's just choose 6. You could use the same point if you'd like. Let's just choose 6. And is equal to the slope of 3/4 times x minus the x value here, which would be 6. And you just simplify this to be y minus 6 is equal to 3/4 x minus 3/4 times 6, which would be, that would be 9/2. 3/4 times 6 would be 9/2. And yeah, all right, so then you add the 6 to both sides. Add the 6 to both sides. And you end up with y. You end up with y is equal to 3/4 x. And then you have the result of negative 9/2 plus 6. Another way to say 6 is 3/2. So here you have negative 9/2. I think I said 3/2. I didn't mean to say that. You have negative 9/2 plus 12/2. Forgive me. So you have negative 9/2 plus 12/2, which is 3/2, which is the same thing that we got here. So we just we obtained the equation the linear model or equation in two ways using two different forms, the slope-intercept form, point-slope form. All right? So that's the kind of thing that we did do last week. All right, so let's look at a slightly different example that's more real life. All right, a slightly different example that's more real, it's more of a realistic, it's more of a realistic example of what we could see in real life. This idea of increasing 3 over and over and over again, going from 3 to 6 to 9 to 12. That's not as it's not as realistic. It helps understand the big picture of what creating an equation is all about. Let's take a look at that. It helps. So with this equation now, if you wanted to ask yourself how many friends will you have after 100 weeks, you could now take that 100, which is an x value, and substitute it here and easily solve for y. All right, so you have y is equal to 3/4 times 100 plus 1.5. And then you'd get, put a 25 here, you get 75 plus 1.5, and then you get 80. You get 76. You get 76.5 friends. You get 76.5 friends. So it's so much easier to have an equation and extrapolate than just counting by 4 over and over again repetitively. So hopefully you see the benefits of this. You could also solve for, with this equation, y is equal to 3/4 x plus 3/2. You could also solve for x. If you had 1,000 friends, how many weeks would it take to get 1,000 friends? If you're continuing to grow in this way. So you put 1,000 here and then solve for x here. I don't want to go through that process. I just want to move on. So hopefully you see the benefits, big picture, of having an equation versus just having the data, and then just sort of using a sort of more of a counting method. So let's do something a little bit more realistic, where you don't have it where your data is growing consistently. All right. So let's say we have x and y. All right. And let's say after 2 weeks, we still have the 3 friends. After 6 weeks, let's say we have 7 friends. Right? Or let's say we have the same number of friends, 3. That's realistic. You don't necessarily increase the number of friends that you have all the time, possibly. Let's say you're maybe a little bit of an introvert. After 10 weeks, let's say you have 5 friends. And after 14 weeks, let's say you still have 5 friends. All right, let's graph that. All right. Get a picture of what we are proposing here. And this idea of wanting to have an equation that models this data. All right. Wanting to have an equation that models this data. All right. All right. See what we got here. All right. So call this 1, 2, 3, 5, 6. All right. All right, so let's continue to call this weeks, and let's call this friends. Uh, all right. Y represents monitoring how many friends you have. X represents the weeks, uh, the week that we're in where you have that set number of friends. After 2 weeks, let's say we have 3 friends. After 6 weeks, we have the same number of friends. After 10 weeks, we have 5 friends. All right. And after 14 weeks, we have 5 friends. All right. So now we have a situation where it's difficult to, it's not exact. You're not increasing it at the exact same amount like you are here. In fact, I think I want to amend this just a little bit. Just a little bit. Let's make this 6. Let's make this a 6. All right, so after 14 weeks, let's say we have 6 friends. All right, so it appears as though you're increasing in the number of friends that you have. You're increasing in the number of friends that you have, but it's not exact as it was over here, where you're increasing after 4 weeks, you're increasing 3 friends. After another 4 weeks, you're increasing another 3 friends. After another 4 weeks, you're increasing 3 friends. It's not as predictable. It's not as predictable. So what we need to do to model data that's not as predictable, what we do is we produce something called a regression equation. We need something called a regression equation, a linear regression equation. And it's not as intuitive as what we did over here. A linear regression equation. All right. And linear regression equation, sometimes I've seen it called a best fit line. All right, a best fit equation. All right. So what is the best linear equation that represents this data? All right, what's the best equation that represents the data points that we have here? Okay. What equation would fit best in between, what linear equation would fit best in between these data points? All right. How do we get that? Well, it turns out that we are going to find the slope, right? Just like we did in this problem over here. And then what we're going to do is we're going to use an approach. We're going to use an approach that is very much similar to what we did here and here. Very, very much similar. Okay? So, the way we're going to find this slope, is to use an equation that looks sort of challenging. The way we're going to find this slope is to look at our data here. We've got x values and y values. Okay, we've got 2, 6, 10, 14, and then we've got 3, 3, 5, 6. Okay, and what we're going to do is we're going to find the averages of these x and y values. All right, so we're going to take 2 plus 6, which is, we're going to take 2 plus 6 plus 10 plus 14, and we're going to divide that by 4. Divide it by 4 to get an average, and our average is 8. All right, this sum was 32 divided by 4 to get 8. X bar is another way to say average of the x's. Now let's find the average of the y's. All right, so we end up with 3 plus 3 is 6, plus 5, plus 6 again. That's 17. I'll divide the 17 by 4. And the average of the y's is 4.25. 4.25. Y bar is 4.25. It turns out to get this regression equation, what we're also going to need is the product of x and y. We're going to need the product of x and y. So the product of x and y is 6, and we got 18. The product here is 50, and 14 times 6 is 84. And in addition to needing the product of x and y, we're going to need x, y bar, which is the average of the products. Average of the products. So we got 84. Let's find this average. All of these numbers here. Okay, so we get 84 plus 50 plus 18 plus 6. We get 158. I'm going to divide that by 4. And my average is 39.5. 39.5. Okay? All right, so we need all of that. We need all of that in order to find this regression equation. We need all of that to find this regression equation. The first step over here was to find the slope. The first step over here will also be to find the slope. But we need a funny looking equation, okay? So I hope it doesn't intimidate anyone. So we need x, y bar minus x bar, y bar over the standard deviation of x squared. So finding the slope over here was fairly easy. The change in y over the change in x. Finding the slope over here is a little bit more complicated, but I think we can handle it. All right, so xy bar, we calculated that, was 39.5 minus x bar, for us is 8, times y bar, for us is 4.25, all over standard deviation of x. Standard deviation is a term that I don't want to spend time talking about what it means, but safe to say you can find it on the calculator. You can figure it out on the calculator. Let's go to edit, and I'm going to find the standard deviation with my calculator. I just need to put in these x values: 2, 6, 10, 14. All right. And let's find the standard deviation of these points. Let's go to stat. Let's go to calc, one variable stats. Then I'll go. I get a standard deviation of 4.472. 4.472, and I need to square that according to this equation. All right. So let's put all of this into the calculator, figure it out. 39.5. 8, at 8 times 4.25. And we end up with 34. And let's take the 4.472. Let's square that. And we get something very close to 20. I'll just put 20 there. Get something 19.998. Let's just round that to 20. And we end up with 39.5 minus 34. 35.5. Let's divide that by 20. All right. Oh, good. Embarrassing. 5.5. Sorry about that. That's a little bit embarrassing. 5.5. And then we divide by 20. Divide by 20. And we end up with 0.275. 0.275. All right, 0.275. That is our slope. That's the equivalent. It's the best representation of the slope for the data that we have. All right. In the same way that we found out the exact slope for these data points, the best representation of the slope for all this data, assuming a linear pattern, would be 0.275. 0.275. Now, in the same way that we found the y-intercept over here, we chose 2 points. We chose the points 2, 3. Over here, we chose the point 6, 6. We could do the same thing, but we'd have to choose the points that we have here. For our points, we would choose x bar and y bar. So what we could do here is, I hope you don't mind me completing the problem up here. So we got y is mx plus b. Y is mx plus b. And we could choose the points 4.25 and 8. So we got 4.25 is equal to our slope of 0.275 times x, which is 8, plus the y-intercept. So we end up with 4.25 is equal to 0.275 times 8. You get 2.2 plus the y-intercept. You subtract that on both sides, and you're going to get the y-intercept is 2.05. 2.05. 4.25 minus 2.2. All right. So now that's our equation. That's our equation. Our equation that best represents this data is y is equal to 0.275 x plus 2.05. All right. So in the same way we use this equation here, we could use this equation here. You could extrapolate and make predictions and forecast what's going to happen in the future after 100 weeks, assuming that the number of friends continues to grow the way it is here. After 100 weeks, how many friends would you have? You could put 100 right here and come up with an approximation, the best approximation of the number of friends after 100 weeks. So I hope this is clear what I'm saying. This is called a linear regression equation. Sometimes it's called the best fit equation. But I think it's more realistic. It's more realistic not to have the consistent slope week after week after week. Things change, you know. Some days you're in a good mood. Some days you're in a bad mood. You don't have an increase of friends. And then some days, you know, you may not increase the number of friends week after week after week. I hope that's clear. I hope that's clear, because it is a valuable, anytime you can take data and get a better feel of what's happening with that data, having the ability to predict what's going to happen in the future. This is what statistics is all about. Statistics are used all the time. Polling, when people are polling and they're accumulating data, talking to people, seeing what people feel about particular topics or issues, and then taking all that data, synthesizing it, and what's called inferring. What does this mean? This is a very, very important tool, very important math tool, statistics, which really is what this is. All right, so that's one topic that I wanted to talk about, and I'm reminded of let's add a little technology to this. One of the things that I'd like to try to do, what I'd like to try to do is put this into our calculator. Let's go to stat again. Let's go to edit. And we've got 2, 6, 10, 14. I don't know if you can see this. Let me try to zoom in more. I didn't mean to do that. There we go. Yeah, there we go. I hope you can see my calculator possibly. You might not be able to see that because of the glare. Let me try to get rid of the glare. Nah, you can't see it. Well, I'm trying to do the best I can to get rid of the glare. So we got 2, 6, 10, and 14. Okay. And then I've got in my column over here, my column labeled L3, I've got 3, enter, 3 again, and then 5, and then 6, okay? And let me delete everything else that's there. And let's try to get this same equation using the calculator, okay? And I'm sorry you can't really see that very, very good. What we can do, I believe, is go to stat, and we can go to calculate, and then let's go to where it says linear regression. Let's go to 4, and we want to find a linear regression using the data. I'm going to call list 1, all right, and then let's put a comma, and then let's try to call list 3, and hit enter there, and amen, look what we got. We got y is equal to ax plus b. I hope you can see that. And then they say a is 0.275. 0.275. Okay? And look what we have here. Look what we have here. We've got 0.275. We got the same 0.275. And then here you can't see it, but b is 2.05 on the calculator. And look what we got here, 2.05. So we teach the students to use the technology. You know, we teach the students to use the technology, but we also want the students to know how to get answers without the calculator. So that's what we ask the students to be able to do. I want to move on to another topic in the same family as what we've done here. And let's just jump into that. I started it before the show. I want you to be able to see that here, what we were doing is we were adding 3 repetitively. Here, what we're doing is we're actually dividing repetitively, okay? Here you're dividing 2, and then you take 3 divided by 2. You divide 2 again, 3 halves divided by 2 is 3/4. So that's another kind of equation, okay? This won't create a linear equation, okay? Now, some would say it's not realistic to constantly be dividing like that. That's not realistic, okay? It's not realistic. And you're correct, it's not. But we want to, I'm starting with what's not as realistic and moving into a more relatable problem later in our meeting today. All right, so we've got, let's say 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. All right. So let's plot this. Let's get a feel on what it looks like when you actually divide by 2 repetitively. Okay. So we've got 6, 6. All right. We've got the point 5, 3. Got the point 5, 3. All right. We've got the point 4. Oh, I plotted that wrong. I'm embarrassing myself a little bit today. I apologize for the mistakes. So we got 6, 6. That was 0, 6. Sorry about that. 0, 6. We got 5, 3. We got 4, 1.5. 4, 1.5. We got 3.75. And this would be getting lower and lower and lower, okay? If I were to go to 2, that would be 3/8, which is smaller than 3/4. All right, and if I were to go to 1, that would be even smaller, 3/16. All right, being lower and lower and lower. So what we have here is called exponential growth. It's called exponential growth. There are things that grow very rapidly. Some would say when we were in the pandemic, there was an exponential growth for a season. The growth of the virus grew exponentially. And this was a big problem, so they shut the whole country down practically. Told people to stay home to avoid the exponential growth that we were experiencing. So this is very relatable. While I'm here with this picture, let's draw something that would look as if it was decaying exponentially. This would be exponential decay. This would be, I'm sorry, you can't see that. This would be an exponential decay. Exponential decay. This would be exponential growth. Okay, this would be exponential. Something is growing from left to right. It's growing exponentially. Okay. An example here. I've been doing a lot of gardening. Something decaying exponentially. I'm doing a lot of gardening, and I dumped some dirt on the ground, expecting it to dissipate. Okay, so at time 0, I put a bunch of dirt in the ground, and what I'm expecting over time is the rain and so forth will break that dirt up. It'll break the dirt up, and over time, after a while, after, let's say, I don't know how much time, but after some time, I'm expecting that dirt to go away. I'm expecting it to dissipate and go away over time. That's off the top of my head example of exponential decay. So some things grow over time, some things decay or dissipate over time. All right. So what would be an equation that modeled this? We need an equation that models something that over time is doubling. When at time 1 to time 2, that item doubled. And then you doubled to go from here to here. And then from here to here, that's a doubling. Here you're doubling. 3 times 2 is 6. You're doubling. So how would you produce an equation that you're multiplying repetitively? You're multiplying repetitively. It turns out that the way you model that is you have y is equal to, let's just call it a b to the x minus 1 power, where a represents whatever your first term is. A represents the first term. A represents the first term. B represents something called a common ratio. B represents a common ratio. All right. And x, x minus 1, we'll just call that an independent variable. All right. So our first term is, let's just use 6. Our first term is 6. So we've got y is equal to 6. The common ratio is the number that is being multiplied repetitively throughout the problem. And that number, let's just say, is half. It's actually, I think I might have, yeah, we'll try it, half. Let's try half. And then we'll say to the x minus 1 power. All right, so this data, here, let's see what we got. So if we put x is 6 here, we get a 5. I think what we're going to do is amend this a little bit. We put a 6 here, we get a 5. 1/2 to the 5th times 6, it won't give us 6. So I'm going to amend this a bit. I apologize. Let's instead start with this point. Start with that point being the first point. So our first term, we'll say, is 3/16. 3/16. The common ratio would still be half. And we'll say to the x minus 1 power. All right. So what are we going to do? So when x is 1, maybe I should have had these terms inverted. In other words, I should have had this term first, this term second from top to bottom. So I apologize for the confusion. Forgive me. So we put in 1 here. Half to the 0 power is 1, and 1 times the 3/16 would give you the 3/16. If we put in x is 2, we'd have half to the 2 minus 1, which is 1. Half to the 1 is half, and we end up with 3/16. We end up with 3/16 times half would be 3/32. 3/32. You put in 2 here, you get 2 minus 1 is 1. You get half. 3/16 times half is 3/32. And it turns out that we don't get the 3/8 that I was expecting here. All right. So I got to see what the issue might be. First term is 3/16. Oh, okay. I really apologize. I really apologize. Our equation again, once again, we got y is equal to the first term times the common ratio. Our first term is 3/16, but our common ratio is not half. Okay, forgive me. Our common ratio is 2. I am so sorry. Common ratio is 2. to the x minus 1 power, because it's 2 that you're multiplying to go from one term to the next. Forgive me. All right, so what we have is we have y is equal to 3/16. 3/16. If we put a 1 here, we still get the 3/16. We end up with 2 to the 1 minus 1 power, and that's going to give us 3/16. All right, so if we put in 2, we have 3/16 to the 2, and we have 2 minus 1 power. 2 minus 1 is 1, and we end up with 3/16 times 2, which is indeed the 3/8. All right. If we put in 3, we get 3/16 times 2. 3 minus 1 that's 2. 2 to the second is 4, so we have 3/16 times 4, which is 3/4. So this equation here, I apologize for the error here. I apologize, and I hope I didn't confuse anyone. But this equation is what models data that is being doubled over time. This is the equation that models data that is being doubled over time. All right, so it's a different kind of equation. This is called exponential growth. This is called an exponential growth equation. All right, this is called an exponential growth equation. All right, I want to talk about one more thing because this is not as realistic. All right, this is not as realistic. Okay, so let's look at an equation that would be more, I said equation. Let's look at a situation that would be more realistic. And rather than do this by hand, because we don't have as much time, rather than do this by hand, let's just put it in the calculator. I really wanted to do this by hand. Next week we'll do a problem. We'll get this same answer. We'll do the work by hand, but for today, I will just use the calculator to get our answer. All right, so here we have, let me just rewrite this data here. The source of my mistake that I made was I didn't put this in the order where I could be clear. So I should have put the 1 and 3/16 first, the 2 and 3/8 next, then the 3 and the 3/4 like so. 4, 3/2, 5, 3, and 6, 6. And if I would have written it this way, the way I should have, it would have been clear. It would have been clear that my first term, here I said my first term was 6. Well, that's wrong because my first term was actually 3/16, like I have here. Okay? And then my common ratio, I said my common ratio here was half. I said that to go from here to here, I was multiplying by half. To go from here to here, I was multiplying by half. To go from here to here, I was multiplying by half. But that's actually not true. The common ratio was here. So sometimes it's okay to make a mistake if you just cross it out. And more than anything, you learn from your mistakes. All right. The thing that I learned is I should have wrote this down in the proper order. All right, so last thing that I would like to show you is what if we had data that you're not multiplying by 2 repetitively? What if we had data where you were not multiplying by 2 repetitively? What if at time 1 you didn't have 3/16? Let's say you had something like 1/4. What if at time 2 you had let's say you had 3/8. What if at time 3 you had 1? What if at time 4 you had 2? At time 5 you had something like 6. At time 6 you had, let's say you still had 6, okay? So we have something that's starting off fairly small, but it's growing. In fact, let's make this even like 16. It's starting off small, but it grows quickly. You're starting off at something that's very low and it's growing quickly. Let me graph that. That's an exponential growth situation. And there are things that are in real life that if you track them, you're starting off with a slow amount. Time 1, you're starting off with a low amount, but as time goes on, it's growing rather rapidly. This is not a linear model here. So let me graph this. I think I need a little bit more space. We thank you for your attention today. We're almost done with the show. Thank you for your attention. Next time, by hand, we'll come up with a exponential regression model of this data. It takes a little time, though. So we don't have time to do it today. All right. So let's count here. 1, 2, 3, 4. I think I'll need a little bit more space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 11, 10, 9, 8, 7, 6, 5, 4. So let's plot these points. We got 1, 1/4, that's a very small number. 2, 3/8, that's a little bit higher. 3, 1, 3, 1. 4, 2. That almost looks like a linear situation up in here. That almost looks linear. But immediately you go from 5 to 6. All right, so there's a sizable jump there from 5 to 6. All right, from 5 to 6. You see that jump, and then you go from 6 to 16. There's a rapid growth there. That's called exponential growth. That's not a linear situation. It looks linear in here, it looks somewhat linear, but the totality of this data is more exponential. So next time, what we're going to do is by hand, we're going to come up with our exponential equation. But for now, what we'll do is we'll just put it in the calculator. We'll put it in the calculator. So we go to stat again. We go to stat edit. And I'm going to put this data into my calculator. I've got 1, 2, 3, 4, 5, 6. And now we put in the y values, 0.25. Another way to say 1/4 is 0.25. Another way to say 3/8 is 0.375. We put in 1, 2, 6, and 16. All right. So yeah, this could be after one. This could be X could be days, right? Y could be cases, COVID cases. All right. When we first started out with the pandemic, X could be days, Y could be cases. Maybe it's not the best example. You can't have a quarter of a case of a pandemic, but I hope you understand what I'm saying. So an equation that would represent the equation that would be the best representation of this data, because it's not perfectly exponential. Here you're multiplying this by 2 to go from here to here, but you're not multiplying this by 2 to get the next point, and you're not multiplying this by 2. It's exponential. It's an exponential growth situation, but it's not perfectly exponential. So the best representation of this exponential data we can get with the calculator. Let's go to Stat, Calc, one variable stats. Oh, no, that's not. Let's go to Stat, Calc. Let's go to exponential regression. I don't know if you can see that. Try to get rid of the glare. Exponential regression. Yeah, you probably can't see it. Exponential regression. Let's hit enter there. Let's try it again. All right. Go to exponential regression. We go to list 1. I also had data in list 3. And we end up with an equation of 0.08 times 2.34 raised to the x power. Okay? Okay? All right. So what could we do with that? What could we do with that? Well, now that we have an equation, we can extrapolate. We can forecast how many cases, how many cases of COVID will we have after 1 year? 365. If this goes unchecked, if it goes unchecked, how many cases would we have after 1 year? Well, now you'd put 365 here and you'd get an answer for Y, an approximate number of COVID cases after a year. Or if you wanted, perhaps what you could do is how long would it take to get 1,000 cases? Well, now that's Y. So you'd put 1,000 here. You'd put 1,000 in for Y and solve for X. All right? So hopefully you see the benefit of having data and taking that data and turning that data into an equation, a best approximation of the data. Having an equation for the data would be beneficial to try to extrapolate. Okay, to try to forecast and predict what's going to happen in the future. Next week, we're going to do that. We're going to get that 0.08, 2.34 raised to the x by hand. And it is involved, but it's nothing that we can't handle. All right, so that's about all we have time for. We thank you for your attention, and we thank you for watching. We hope you enjoyed the show. We hope you learned something, and we hope you'll look for the shows. We don't have a regular schedule as we have had in the past, but look for the shows, Dominate Math, where what we try to do is encourage students to put forth their best effort. We try to encourage students not to quit. We try to show how math can be connected to everyday life. We hope you enjoyed the show, and that's all we have time for right now. Take care and keep watching. Thank you. Have a good evening.